Okay, so let us start this last part of this very long chapter, and that is mathematical induction. So what is mathematical induction? So the idea, I don't know how to explain it for you, might be that is easy to understand from this language. So let us say that you have stairs in front of you, a lot of stairs, that you number them with natural numbers, and this is the floor. So, and then you have step number 1, and that's stair number 2, and then stair number 3, and then you can continue this, for example, and this is, for example, this is stair number k, and the next one, of course, becomes k plus 1, and then you continue like that. Okay, so this is what I want to tell you is this. So let us say that you have a toy or whatever. You know that the toy, when you put the toy here and it moves here, someone guarantees you that this toy can climb the first stair. Okay, let us assume that this is guaranteed. Okay, you have by the manufacturer or whatever you want to buy this toy. So on the toy, on the catalog, it is written that this toy, if you put it on the floor level, this toy can climb the first stair. This is guaranteed. And the second thing they are guaranteeing you is that if this toy is on any stair k, we guarantee that it can go to the next stair at least. Okay? So using these two together, what do you think? Do you think that what you are buying is capable of climbing all these stairs or not? Yes, is that clear? Because it is guaranteed that this toy can climb the first stair. This is the first statement guaranteed by the manufacturer. The second statement tells you that if you put this toy directly on any one of these stairs, say the stair number k, we guarantee you that this toy can also climb to the next level. Okay? Now, using these two informations together, you can see that, okay, this toy actually can, if you put it on the floor, it will continue climbing all these stairs one after the other. Why? Because it is guaranteed that it can go to the first one, and it is guaranteed that if you put it somewhere, it can go to the next step. So now if it climbs to the first one, because it can go to the next step, it can go to number 2. Now it is on 2, because it can go to it can climb one more step, it goes to 3, and it will cover all these stairs. Now, is it understandable? Yes. So that is the meaning of mathematical induction mainly. So if I want to formalize it, so we say that let P of n be a statement regarding a natural number n. Okay. So that, okay. So this toy was guaranteed to go to the first step. In the language of mathematics, we say that P of 1 is true. I will explain them if you don't understand, don't worry. Number 2, if k is a natural number such that P of k is true, then P of the next number, k plus 1, is true. Okay, so let us imagine. P of n is a statement regarding a natural number. I'm telling you something about natural number n. But when you check this statement for n equals to 1, you realize that it becomes a true statement. And the second thing is that if P of k is true for a given natural number k, you realize that the same statement for the next number, k plus 1, is also true. Okay, so if I guarantee you these two things, for example, let me write, if you want to understand better, so let me write Pn, 2 to the power of 3n minus 1 is divisible by 8. Okay, so this is claiming something. Okay, but n is a natural number, so let us say that n is a natural number, and then I write this statement in front of you. I am claiming that for any natural number n, 2 to the power of 3 times n minus 1 is divisible, by 7. Okay, so I'm claiming this. So this is a statement regarding a natural number n. It might be true or might be false. Okay, but this tells you that you check P of 1 to be true or not. So let us check. Do you think this statement is true for n equals to 1? So you have to check it out. You replace n with 1. You get 2 to the power of 3 minus 1, which is equal to what? 7. And so you say that 2 to the power of 3 minus 1 is divisible by 7. Is it a true statement or not? It's a true statement. So you see, that is what I'm saying. When I say I have a statement regarding a natural number n, exactly I mean like this. Okay? When I say a statement, I have a declarative sentence which claims something. It might be true or might be false, but let us say that what they are claiming is true at least for the first number. Okay? And then, this is important to understand. Then it tells you that let us assume that this is true for a number k, whatever k is, it's a natural number. I show that this statement, which is assumed to be true for number k, I show that it is also true for the next number only, k plus 1. Okay? Now, do you agree with me? If I can prove these two things together, then it means that this statement is true for every natural number. I want you to understand that. Yes? Because this tells you that P of 1 is true. This tells you that for every k, if P of k is true, it is guaranteed that P for the next number is also true. Okay, look at them together. P of 1 is true, so it means that because of the second rule, P of the next number is also true, which means P of 2 is true. Yes?
Doesn't the second rule work by itself? Like, is the first rule needed in this case?
Yes, I will give you examples. Okay? So here, if I want to answer your question, this is more or less needed. If you just read on the catalog that this toy, if you put it on a step, on a stair, it can go to the next step. It is not guaranteed by this statement that if you put it on the floor, it will climb all the stairs. Is that understandable? Because the second one tells you that if your toy is here, or if your toy is any one of these levels, it is guaranteed that it can go to the next level. This by itself does not guarantee you that if you put the toy on the floor level, it will climb all of them. Yes, because it might come here and then cannot climb the first one. But if it can climb the first one because of the second rule, then it is guaranteed that it will climb everything up. Yes. So this is why we think. I give you a statement regarding a natural number, and I want you to prove it. Okay, one way of proving this is, of course, whatever we learned before, direct proof, indirect proof, but one important tool in our hand is the mathematical induction way of proving this. And if you want to do this, you have to check this statement manually for the first natural number n equals to 1 to see if it is true or false. Of course, if it turns out to be false even for this first step, so it means that this claim is generally false. Okay? Now, if the first one is true, you yourself assume that this one is also true for number k, and I try to show that this is also true for the next level, pk plus 1. If you succeed to do this as well, these two together guarantee you that this Pn is true for every natural number. Is that clear? Okay, so let P of n be a statement regarding negation so that these two, then P of n is true for every natural number n. Okay, so that is, I don't want you to memorize that, I want you to understand that. So is that clear that this makes sense? Yes? By the way, this is a mathematical induction. So you know that in science we have two philosophies, yes? So induction, inductivism, and reductionism, yes? So this is the way that we do things in science. Reductionism is that if you want to study something complicated, we break it down to pieces, study each piece of it, with the hope that if I understand the constituents, then I add them up somehow, my knowledge will somehow describe the whole thing. So this is at least what science works, I don't know. So this is the philosophy behind scientific method. And the other one is inductivism. So what does it mean? It means that you do some experiments case by case because you cannot cover everything. So you want to see, for example, if the universal law of gravitation, which introduced by Newton, is correct or not. You have to do some experiments, okay? And if you repeat your experiments, say 100 times, 1,000 times, and if it works every time, then suddenly you say that it seems that this is the law of nature, so let us take it for granted. So I want you to see that's also inductive way. You start from small pieces and say something in general. Okay, so in science we also have induction and reduction. Okay, but I want you to understand in science we expect that something happens that falsifies our theory or our rule, yes, as it happened for Newtonian mechanics. Because we didn't cover everything, of course. We did experiments for some few number of things, phenomenon, and then I realized that, okay, it is working. Then I said that, okay, it will work forever. And every scientist knows that might be one day they can find a counterexample for the theory. Okay? But this is the way that we can do it in science. I want you to understand this is not the way that we do it in mathematics, even though the name is induction, but that is a real proof. So if you can prove something using mathematical induction, it has the characteristic of mathematical theorems. It will live forever. Okay? So it is not like science induction. Science induction is like this. For example, I go to a city, the first person I encounter is blind, and then I want to ask an address. Okay, he or she cannot read it. Then the second person comes in, I want to ask, I see that that person is blind, and it repeats itself several times. Then I come back home, I said that I was in a city, everyone was blind. Okay, this is the way that science do the induction. Of course, it was clear that might be another person after some time. There will be that person is not blind. Yes. So this is why I'm trying to say more or less that is also inductive way of conclusion. I see some small things and then conclude something in general. This is also the same for mathematical induction, but mathematical induction is true, and if you can prove something using mathematical induction, it is not like the example of blind people I just mentioned. It means that this is forever. Okay. Of course, there are two parts for this problem. One, understanding why this machinery works, and the other one is improve your skills to do that. Yes?
How did you conclude that Pn is true for every not?
No, that I want you to understand. So you see, I have a statement. I say that this statement is true for the first number 1. Yes? This I can check. Then if I can show that if a statement is true for k, then it is also true for the next number k plus 1, then together it means that it is true for every n. because it is true for 1. Okay, I check it manually. And then I prove in general that I am able to go from level k to level k plus 1, whatever k is. Okay, this means that I am on level 1. When you say P of 1 is true, it means that I am on the first level. In the second step, I show that whatever level I am guaranteed to be able to go to the next level. These two together, it means that I can climb these stairs from the beginning to the end. And this means that P of n is true for every natural number. Okay, first I want to think about it. Yes?
Is this a type of agreement we talked about in the last lesson, like premise and conclusion? Is this related?
Somehow it might be related, but not directly. I don't exactly understand what you mean. But I mean, don't make it so hard, okay? So I have a set of levels in front of me. I guarantee you that you can climb to the first level. This, okay, just this one, if I stop, is it guaranteed that you can go to the all levels? No, not yet. I guarantee you, yes, you can go to the first level. And then I guarantee you that if you are on any one of these levels, whatever it is, I guarantee you, you can go to the next level. These two together, it means that you can climb all these stairs. Yes?
But if it's true for k, does that mean it has to be true for every number before k?
No, that's exactly what I'm saying. No, this is not assuming something before, or it is just assuming between level k and k plus 1. If you are on level k, but whatever k is, okay, then you can go to the next level, k plus 1. When I say if k is a natural number, it means that I haven't fixed the k. I am just telling you that if you are on a level k, whatever k is, you can go to the next level, k plus 1. Okay? And the first one, I am guaranteeing you that you can be on first level. Okay? This tells you that you can be on the first level. This tells you that if you are on level number k, whatever k is, you can go to the next level, k plus 1. These two together means that you can climb all these levels. This means that my statement is true for every natural number. Yes? Is that understandable? Is it hard or not? Yes?
But I'm just thinking, then couldn't you just choose k yourself, whatever number you want, and then the number afterwards?
No, if I choose a number, for say 5, and I show that I can go to next level 5, that's it. 4 5s, okay? 4 5. But I don't choose a particular value for k. I am saying that whatever you choose for k, and you are on the level k, I guarantee you that at least you can go to the next level, k plus 1. But if you fix your k to say 4, and then you show that I can go to 5, so then, yeah, you did something. You showed me that you can go from 4 to 5. And you showed me that you can be on 1. Okay, then what? You see, this process will break. But if I don't choose k, I say whatever k is, if you are on level k, you can go to level k plus 1. Okay? And then I guarantee you that you can be on level 1. You can use these together, and then you say that, okay, I can climb all the trees. Why? Because I guarantee that you are on level 1. In the second step, I tell you whatever you choose for your level k, you can go to level k plus 1. Okay, so you take the level 1 first, you climb the first one, and then you use this machinery. You say that now I choose my k to be 1, because k was not specified here. I can choose whatever I want for k. So now I choose k to be 1, so I go to the next level 2. Now that I am on level 2, I choose k to be 2, so it will help me to go to level 3. Okay, so you should say that whatever k is, for every natural number, you should show me that you can go from this step to the next one. Yes? Okay. So, for example, let me give you a very classic example. Every book, actually, when they want to talk about mathematical induction, they usually start from this. We want to prove this using mathematical induction. We want to prove that for every, so I would say let me write it properly. So example, let n be a natural number. Okay. Show that. So I can, of course, I have to write, but using mathematical induction, show that if I add numbers from 1, 2, 3 up to n, this becomes n times n plus 1 divided by 2. Okay, so here I have given you a very famous formula that you already know. And if you remember, we had this when I was teaching you arithmetic progression. That is the sum, because this 1, 2, 3 up to n forms an arithmetic progression, and we learned how to find the sum of the first n terms, Sn, yes? And that was actually the Gauss problem. But now we want to prove it using mathematical induction. So the first thing that you do if you want to prove mathematical induction is to take your statement and call it P of n. Okay? So this is a statement regarding a natural number n. Okay? And then you need to follow these steps. This is called mathematical, this is called inductive base. Yes. So this is the base of induction. I check the claim for just n equals to 1. Okay, so let us check. What is the meaning of checking the statement for 1? It means that you replace n with 1, it becomes a statement, and evaluate it. Is it true or false? Okay, so you have to rewrite your statement, which was a statement for n. Now n is given to be 1 to you, so you have to rewrite your statement, but this time consider that n is given to be 1. Okay, if n is equal to 1, of course the right hand side is simple. If n is 1, this will be my right hand side. What will be my left hand side? Because if I give you n, how do you write the left hand side? You will start from 1. For example, if I give you n is 3, so you start from 1, 2, 3. So you see you have to go up to n and then stop. But if n is already 1, whenever you start writing 1, you have already reached to the end. Yes, so it means that the process stops. So P of 1 is this statement, okay? Okay, first of all, what we do, we take what is given and call it P of n. The first thing we need to do is replace n in the statement given by number 1. Of course, you have to think a little bit to write it correctly. If I want to check if I replace n with 1, the right hand side doesn't pose any problems, yes, because I just take n out and put 1. And for the left one, you have to interpret it a little bit, because when I give you n, you are supposed to start from 1, go 1 step 2, go 1 step 3, and then continue this pattern until you reach to the given number n and then stop. But when I give you n equals to 1, you start from 1, but you are supposed to reach to which number? To 1, so it means that this is done, this is finished. Okay, so now is this a statement true or false? This is a statement. This is claiming that 1 is equal to 1 times 1 plus 1 divided by 2. It might be true, might be false, but in this case is true. Yes, because if you calculate 1 plus 1, 2 times 1, 2 divided by 2, 1, the left hand side 1, the right hand side 1, so is true. So it means that the base of induction is checked and it is working. Okay? Now the next part this is a little bit. I want to understand exactly what's going on. So for the next one, what should I do? I would say that let k be an arbitrary natural number such that p of k is true. Yes, we show that p of k plus 1 is also true. Yes, I write this, I don't write it, so you write it in the exam, but I will not write it over and over again. This is always the case, okay? So if you want to write the second one, this is just a sentence that you need to use. So is that clear? I am taking k, I imagine k is a natural number, but arbitrary. Yes, it doesn't matter what number it is, it's whatever you want to, but it's a natural number. And I myself assume that p of k is true. Okay, it doesn't mean it is true, it doesn't mean it's false. I am assuming that this is true. Okay? Then I show that then p of k plus 1 is also true. Okay? So this is the way that you have to think about it always. Okay, so then your duty is to write p of k, because I am assuming p of k is true, so I have to translate this in the language of the problem given to me. So I need to know what p of k is. I also need to know what p of k plus 1 is, so that I know what to do. Yes? So what is p of k? P of n is this one. P of k means the same statement. The only difference is that instead of letter n, you have letter k. Yes, is that clear? So I will rewrite the same expression. So 1, 2 plus 3 up to which number? K equals to. So let me write this. I want you to write in the exam. So assumed to be true. Yes. And then p of k plus 1. What is p of k plus 1? I have to rewrite my statement, but the role of n is now given to which number? K plus 1. So you need to write it. So can you help me to write what? So the right-hand side is very clear. So here, whatever I have on the right-hand side, I will replace n with k plus 1. Because when you say p of n, you use letter n. Now I am saying p of k plus 1. So it means that k plus 1 will play the role of this n. So this becomes n plus 1, this becomes k plus 1, this becomes k plus 1, this becomes k plus 1. But k plus 1 plus another 1 becomes k plus 2. Yes? So it becomes k plus 1. Okay, first tell me, do you have any problems from on the right hand side of this? Do you agree? For pk plus 1, the right hand side becomes this? Yes or no? Okay, so what should I write for the left hand side?
1 plus 2 plus 3
Up to k plus 1. Yes. So that is, this is not something mysterious. Of course, I put a pair of brackets because I want to show that this is the whole thing. So this is to be proven. So these two phrases I want you to write in the exam, okay, because it shows that you understand. To be proven. It is not proven yet. This is taken for granted, assumed to be true. And just my duty is to show that if this is true, this one is also true. Is that understandable? Okay. Now, this is my goal. I want to show that this is true. There are different methods of proving things that you have learned before. For example, here I want to show that the left-hand side is equal to the right-hand side. So one way of doing it is to start from the left-hand side, do mathematically valid things, and use my assumptions, whatever they are, and try to help myself to reach to the other side. That's one way I do it, okay? So let us just do it together. So be careful, don't get confused. Your goal is to prove this. So I would say that the left-hand side is equal. So let me write it in front of our eyes. 1 plus 2 plus 3 up to plus k plus 1. This is the left-hand side of what I have, okay? But do you agree with me? Because I am going one step at a time. If I continue this list dot 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 and I reach to k plus 1, what is the number before that? When I reach to k plus 1, definitely I will pass k. Yes? So this is helpful. You see, you don't need to write it here. But when you want to prove something, you need to help yourself to think, okay, when I have reached to level k plus 1, according to this pattern, it is clear that exactly before reaching to this, I have covered k. Yes? Why did I ask you to write this down? Because then it becomes clear what to do. Why? Because instead of this one, what can I write? Yes, you see, assumed to be true. So this means 1 plus 2 plus 3 up to k is k times k plus 1 over 2. So instead of that, I put k times k plus 1 divided by 2 plus the next one, k plus 1. Yes? So this one, but the assumption, yes? The inductive assumption. The inductive assumption means this one. So this, I can take it out and put this one here, and then I copy it and paste it this one. But my goal is to reach to the right-hand side, which I haven't yet. Yes? But then this becomes a simple algebra. So what do you think I will do? My goal is to reach to this expression. So far, I have reached to this expression. So what do you think might be helpful? To continue this algebra, simple algebra, and reach to the right-hand side. So what should I do? Yes?
If we write it as k plus 1 with the denominator.
2. Yeah, so it becomes exactly. So this becomes the common denominator, k times k plus 1 over 2. This I will give a denominator 2. I want to make the denominators the same, so I multiply this by 2 as well. Now that the denominators are the same, what can I do? I put 2, and then I add this one to this one. So it becomes k times k plus 1 plus 2 times k plus 1. Yes? And now k plus 1 and k plus 1 is a common factor, so I can pull it out. From this one, k plus 1 is pulled out, k is left. From this one, k plus 1 is pulled out, 2 is left. And then divided by 2. Is this what I want? Yes. That's exactly equal to the right-hand side. Okay. It's like a magic. The only thing that I want you to understand is that this is valid argument, not circular argument. Let me try to motivate you to be skeptic about it. Because you might say that, Bob, like this is ridiculous because you want to prove this. So it means that you don't know if this is true or false. You want to prove this is true. Okay, and now suddenly you are changing the letter n to k and then ask us to assume that this is true. So are you crazy or what? I want you to understand this is not a circular argument. It is a complete valid argument. So this is the important thing. Of course, you can start learning doing it like a robot without understanding and it will work. But I want you to understand, I am not cheating. It is working. You see, I want you to understand exactly this point. You see, I want to prove this for letter n, okay? N is a natural number. For any n, a natural number. So it means that I don't know if this is true or false, okay? But now what I'm doing here, it seems like this. I am changing the letter n to k and write exactly the same formula, and I'm demanding, assume that this is true. Okay, but I want you to understand this is not what I am doing. I am saying that this is still this here. This has a chance to be true or false here. I don't care. I am caring that if this is true for level k, the same statement remains true for level k plus 1. but it doesn't mean this is true. Assuming that this is true is different from it is really true. You understand what I mean? Yes? So I'm saying that if you assume that this is true for number k, it might be false at this level. What I'm claiming that if you grant this to me, I can grant the next level. But it doesn't mean that this is really true. Okay? So I'm just telling you that if in any way you are on level k, how you reach to level k is not my problem. You are on level k, I prove you that you can go to level k plus 1. But this is exactly what we are doing. I am saying that assume that this is true, might be false, I don't know. Then I show you that the next one is also true. Yes?
But if it's false, then the next one will also be false, right?
No, I don't want you to think in that way because it brings a lot of confusion. So what I'm trying to say is exactly compare it with these levels. I'm telling you that if in any way you can reach to level k, how you have reached to level k is not my problem. Okay? So let us assume that there are two people. One people is responsible to checking that if you can climb the first step. Another person is having a little bit harder duty. He wants to check if in any way you have reached to level k, you can also go to level k plus 1. But this is not his problem that if you really can reach to level k. Yes? So that is exactly what we are writing here. When I write this assumed to be true, I am not writing it is true. I'm saying that, okay, assume that this is true. I want to show that the next level can also be taken. Yes.
But then if you can't, so you're also saying that if you can't reach level k, then you can't reach level k plus 1 too.
No.
But you just proves that if one is true, then the other is also true. So if one is false, then the other is also false.
No. That is, I'm not discussing about your argument. Even if that is what you are saying is true or false, it is irrelevant. I don't want to make trouble for myself. I want you to focus on what I am saying and realize what I'm saying is logical. Might be you open a lot of possibilities that I have to think about them. Okay? But my point is that I am just telling you that, you see, there are two people. One people check if you can go to level 1. Okay? So it means that if that person sees that you climbed level 1, that person's jobs is finished, he goes home. Okay? The second person doesn't even see you. Okay? The second person assumes that in some way you have reached to level k. Okay? The first person waits and see that you really climb level 1. Okay? The second person doesn't even wait for you, doesn't care about you. It is just in an imagination. That person imagines that some way you have reached to level k. How he doesn't know? He doesn't even know that you really can reach to level k. He doesn't care. What he cares is that in any way, if you have reached to level k, that person grants you that you can also go one step higher. Yes? Then together, this person reports to the manager, the second person also reports to the manager decides that yes, now this person can climb all the levels. Is that understandable? Okay, so if I want to give, but this is a very powerful method. Why? Because it seems that we are using the problem to solve the problem itself. Yes, so that's why it's so powerful. You see, let us say that I want you to prove this and you don't want to use mathematical induction. Do you remember you have to be as smart as Gauss, who was able to invent writing this the other way around, adding them up, dividing by 2. Do you remember? So you have to be creative. But in mathematical induction, you just follow some rules. Being creative is somehow hard. But using the problem, apparently, to prove the problem itself is not that hard. You see, here, this problem is still hard, but I am not empty-handed because I have this assumption in my hand, I can use this assumption to prove this one. But if I want to prove this directly without mathematical induction, then I have to think, okay, how can I do that? Do you remember we did this? We have to be creative to write this from the n minus 1, n minus 2 up to 1, and then add them up and then divide by 2. So then you have to be creative to do something. But here, you don't need to be that creative. So it seems that you're using, it seems, but I want you to understand, there's no cheating. This is completely logical. Okay? So for example, let me give you an example that shows you that this step is crucial. So you cannot drop it, okay? So let me wait. Any questions for understanding this? So that is the solution. If that problem is given to you in the exam to prove this expression to prove this identity using mathematical induction, these blue ones that I have done is the complete solution. Yes?
And we disprove a statement with the mathematical induction.
No, this proof means you need to bring a counterexample. So we discussed about that. What kind of quantifier you have? Is it existential quantifier or is it universal quantifier? So if you want to disprove something, that's a different story.
Yeah, but if we assume that pk is true, but we can't prove that pk plus 1 is true, doesn't that mean
This is a very big step. When you say we can't, it's a very fuzzy phrase because some person can come in and say, okay, you can't, I can. So the notion of can't is not that easy to grant in mathematics. Because you can't, it doesn't mean it cannot be done. It just means that you didn't, you couldn't, yes? That's exactly what it means. Okay, so let me try to give you an example. For example, let me show you this. I want you to see that these people who are working on these two projects, they are needed for this project, okay? Of course, the duty of the second person is harder. It might be his salary is higher, we don't know. But we have to have both of them. Let me try to, exactly it comes to my mind now. Let me just do this. Let me ask you to prove this. Okay, equals to this one. Okay, so let me write it in a way that you can immediately understand, yes? Okay, so let us imagine some person has given you this problem, that person needs you to solve this problem, prove this problem. Is it true or false? It's false because we proved that the correct one is that one, yes? The correct one is this one, so this 2 cannot be there. So this is the wrong one. But I want you to understand the second person still grants it. Yes, the second person doesn't have any problem even with the wrong one. That is exactly what I want you to understand. Let us check. So let us give this person to this company. We have 2 people working on this project. Let us assume that this person is in sick leave and this person is working. This person will grant this again, even though it's a wrong formula. Okay, let us check. So how this person tries to understand this problem, you tell me, because if you tell me, it means that you understand. So because in this project, we call it what? We call it P of n. Okay, let us assume that this person is ill, it didn't show up, and this person is working on the project as usual. So what does this person do? This person assumes that P of k is true. Okay, so it assumes that 1 plus 2 plus 3 plus up to which point k is equal to k times k plus 1 plus 2 divided by 2. Assumed to be true. You see, this person is doing his job. He doesn't care about the first person. Assumed to be true. Yes? And then he wants to see if it is possible to prove the next one. The next one is what? 1 plus 2 plus 3 plus up to k plus 1 is equal to, can you write it the right hand side?
k plus 1
K plus 1
times k plus 2
k plus 2
plus 2
plus 2 divided by 2. To be proven. Yes? I want you to see that these things can be done independently. So this person does not need to wait that person become better and comes back. He can start his job to see if it works or not. Okay? So let us see if it works or not. So he wants to see under this assumption to be true, is it possible that I can go to the next step or not? So that person starts from the left-hand side as before. So it writes 1 plus 2 plus 3 up to k plus 1. And that person, of course, has experience. So know that when it reaches to k plus 1, the previous one is k. Okay? And then this time, what do you think he will do? He will take this part off and put what inside? Put what?
pk.
This one. Yes? So it is k plus 1 divided by 2 plus 2. Yes? This is what he is able to put instead of here because he has assumed that this is true, but then he realizes that he had to add this one as well. Okay? And then take the common denominator as before. Plus 2, and then 2 times that one. Is that understandable? So I just copied and pasted this one, and I take the common denominator as before. And now what happens between these two, I can factor a k plus 1 out. K is left from here, 2 is left from here, and another 2 is left out, and then divided by 2. What is this one now? That's exactly the right-hand side. So you see, I want you to understand what is going on. This person is still reports to the manager, yes, if you are on level K, you can go to level K plus 1, as we did before. But this one is a false statement. He doesn't care about if this is false or not. He just say that, okay, if you grant me this to be true, I can tell you that you can go to the next step. But that is your responsibility if this one is true or false. Is that understandable? So this is why I come back to your question that P of 1 is necessary. Okay? So that person does the job and reports to the manager. Yes, it is possible to go from level K to level K plus 1. Okay? But that person should also report to the manager. When he's better and comes back to the office, he has to check P of 1. Okay? So then he comes and check P of 1. What is P of 1? Can you help me? P of 1. The right-hand side is clear. What is that? 1 times 1 plus 1 plus 2 divided by 2. Okay? And then what happens here? The left-hand side becomes 1. Is it a false statement or a true statement? This is false. Okay? So this means that the inductive base is false. So actually whatever he did, it is in vain. It is not useful at all. Because if that person was not sick and was in the office and checked this one, this even didn't bother to start checking the project. But I want you to understand, the second person is still granted. He reported to manager, yes, if you are on level K, you can go to level K plus 1. Even though this is really false. Do you understand what I mean? So it is extremely important to understand what is the meaning of assumed to be true. Assumed to be true, it doesn't mean exactly it is true. And this is why it's not a circular argument. Because if assumed to be true means to be true, then there is nothing left to prove. Because the difference between these two is just a matter of the name N and K. Is that understandable? So it's a very, do you think I need to repeat? Yes, because you need, I want you to say that as the phrase assumed to be true doesn't necessarily mean it is really true. This is our imagination. We say that, okay, let us assume that this to be true. I want you to understand, assumed to be true and it is really true are not the same things. Yes, because if assumed to be true means is true, then it is a circular argument. Because the only difference between what you see here on the board and what you are supposed to prove is just a matter of the name of the variable, n and k. Okay? And I am still not sure this is true. Okay, so I am not saying this is true. I am saying that let us assume that this is true. Let us check. This assumption grants me being able to go to the next level. You see that in this case it granted, but it was also really true. In this case, it is also granted, even though it was completely false. Yes.
So do we change the letter because we can't just assume that n is true?
Yeah, these are technicalities because in the book, instead of letter K, they use letter P. But because I want to use P here, I don't use P. Yes. I mean, it is not that hard, by the way. Induction is a hard thing sometimes if you really want to understand in a good way and be able to understand. So I want you to, this is my point. By giving this example and that example, I want you to really understand I am not inside a loop repeating myself. That was my goal. Okay? Is that clear for everyone now or not? Okay. Okay, so you see that, I remember that you asked, is this necessary in the beginning? Of course, you were convinced by my explanation, but this is now revealing itself even in a serious way. So you see that the second one, even for the false one, is working. The reason is that P of 1 is really needed, okay? So this just grants you that if you are on level K, I don't even care if you really can reach level K. My job is to grant you, if you're on level K, you can go to the next step, that's it. But is it really possible for you to be on any level? That is not my duty. The duty of that thing is from the first person. And then together, if both of them are granted simultaneously, then I am allowed to conclude that whatever you wrote for n is valid for every n. Okay? Is that clear? Okay. So this is one type of example. Okay, now let me talk a little bit about, there are two weaknesses, being weak, of mathematical induction. Can you see what are those weaknesses? Yes?
Can disprove something?
This is a very general argument. No, I mean, yes.
Isn't it that, like, in some statements, maybe P1 is true, but like,
No, this is not the real healthy. So might be my question is not very. I mean, there are. So, for example, one weakness is that you cannot use mathematical induction in every part of mathematics. You can use mathematical induction only for statements regarding natural numbers. Yes, of course you can do it also for integers, negative integers, but that's not part of your lesson. But I hope that you agree that you cannot use it for fractional numbers. Yes, because when you go from k to k plus 1, you are losing a lot of numbers in between if you want to think about rational numbers. Yes, so if I want to talk about something, if for example x supposed to be n supposed to be a real number, then of course if I go from a step k to a step k plus 1, there are infinitely many numbers between k and k plus 1 that I'm not considering. Yes, so that is one weakness. So whenever you have a statement regarding a natural number only, so let me emphasize here, you can think about proving using mathematical induction. That is one weakness or limitation, whatever you want to call it. But another weakness is what? It is not productive. You need to have the correct formula and then prove it. Okay? So you remember Gauss didn't know the right-hand side. By the way he thought, he was able to generate what is the right-hand side. Okay, so it's superior. But in mathematical induction, you have to have the formula in its entirety, or you should have an educated guess what the formula is, and then prove it using mathematical induction. Okay, Is that clear? So that is also a weakness. For example, I cannot say prove this. This is meaningless. I have to give you a statement in its full entirety, and then I ask you prove that this is true. Okay? So for example, let me give you another example that you understand that this second weakness somehow can be overcome. Okay? It is not always granted, but let me give you an example, which is in the book. I change it a little bit so that it fits to what I'm trying to say. Okay, so let me write an example. Consider the following sum. I would say let n be an integer. Let n be a natural number. Consider the following sum. The sum is 1 over 1 times 2 plus 1 over, the times should be typed here. So 2 times 3 plus 1 over 3 times 4. Let us continue this list. 1 over n times n plus 1. So this is a sum. Yes? Part 1. Determine a closed formula by closed formula, I mean write something which is equal to this but does not include these dots. Determine a closed formula for this sum. Okay, in terms of n. Okay, so don't write part B yet. Okay, so do you understand that I cannot ask you prove the following sum using mathematical induction? Can you understand that? I'm not allowed to ask such a nonsense. Because when I say prove, I need to give you a statement and then you can prove. This is not a statement, this is just one expression. You see, 5 is not a statement, but 5 equals to 7 is a statement. It is claiming something. Yes, this is not claiming something, so I cannot ask you to prove it. It's not claiming something, okay? So this is why I'm asking, determine a closed formula for this sum in terms of n, okay? And then I will add part B. Okay, so how do you think I will do that? One way that human brain works is to consider special cases with the hope that we can find a pattern. Yes? So what you do, this is one way that mathematicians actually discover really regular patterns. Okay, so they say that, okay, I want to find something for this. The first thing comes to mind, let us check. You can go to scratch paper or just the solution. So you say that let me put n equals to 1 and calculate this sum. Okay, let us see what happens. And then, of course, it is not enough. I give n equals to 2, n equals to 3, n equals to 4, and calculate this sum for these numbers with the hope that by looking at the results, I can come up with a pattern. Okay, so let us just do that. If n is equal to 1, what do you think this number be? If n is equal to 1, what is the result of this sum? 1 over 2, yes? Because how this sum continues, when I give you n, you start from 1 times the next number, then you go 2 times the next number, then you go to 3 times the next number, and you continue this list until you reach to the number n that I give. And then you stop, yes? Now that I have given you 1, what do? You again start from 1 over 1 times 2, but you immediately reach to the end, and you stop. So when n is equal to 1, what is your sum? It is just simply 1 over 2. Okay, let us test your understanding. What happens if n is 2? Some students make some mistake when n is equal to 2. Yes?
1 over 2 plus 1 over 6.
Yes, so you have to consider both of them. Some students think that they take only the second one. Don't get confused, yes? Because again, when I give you n, you will start this list from 1 until you reach to my n. My n here is 2, so you again start from the beginning, but this is not enough because you haven't reached the 2. You go to the next step and you reach to the number that I gave you, so you stop. This means that you have to write this. So it is 1 over 1 times 2 plus 1 over 2 times 3, which is 1 over 2 plus 1 over 6. If you take the common denominator, so it becomes 3 plus 1, which is 4 over 6, and you simplify it, it becomes 2/3. Okay, so might be the pattern is not that clear. Let us do the next one. So if n is equal to 3, I give you n equals to 3. You start every time from the beginning and you go at one step at a time so that you reach to the number that I gave you, in this case 3. So it means that I need to consider these 3 numbers. So it becomes 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. And then it becomes 1 over 2 plus 1 over 6 plus 1 over 12. And then I take the common denominator. This becomes 6 times 2 times 1 times, so it becomes 9 over 12, and then you simplify 3 over 4. So now, do you think the pattern is revealing itself? I'm lazy to do the next one. Hopefully, you can see the pattern. Yes, is the pattern clear? When n was 1, the answer was 1 over 2. When n is 2, the answer is 2 over 3. When n is 3, the answer is 3 over 4. So you come up with a guess. Okay, so you say that we guess that this sum is equal to what in general? Can you tell me? N over n plus 1. Okay, so this means that you have a candidate for the answer. So I write it with blue. So we don't know yet. You see why we don't know yet? Because the word guess. Okay? So I guessed something. So, and in this way, I actually make up for the weakness of induction now. Yes, you know? Because now I can use induction to prove it. Is that clear? You might say that, okay, why I need to bother to do it with induction because it seems this is working. But I want you to do that. If you don't do that, it is just a guess. It doesn't matter how many numbers you check. You might say that this is wrong, but when I was doing my PhD, there was some problem I don't remember exactly. It was working up to 1 million or something. So the first thing that doesn't work, it was after 1 million. So let us say that you start doing things up to some 1 million cases, it works. Then you say that, okay, it is clear. Might be if you are a novice mathematician. I mean, if you don't think mathematically, you might say that this is enough. So why should I bother? Okay, but I wanted to understand that from mathematical perspective, it doesn't matter how many numbers I check, and it doesn't matter if all of them are true, but this is still considered to be a guess. Yes? Is that clear? So then it means that this is just a guess, but can I use mathematical induction now to prove my guess? The answer is yes, because I have it in its entirety now. So this is sometimes you find the pattern and you write it there and then try to answer that one, yes. And then use the mathematical induction to prove it. So I will write part B now. So use mathematical induction to prove your guess. Use mathematical induction to prove it, to prove your formula, to prove the correctness of your formula. Okay, we have a little bit of time, so let us finish this one. So I want to clean this. This is given in the book. In the book, they have directly asked you to prove this using mathematical induction. Okay? I wanted to just tell you that it is not that weak. So I mean, sometimes you can find a pattern and use mathematical induction to prove it. But now, let us take, this is the example in the book, let us try to prove it together. So what is the first thing that you should do in mathematical induction? Yes?
call it Pn first, yes? So, yeah, let me not be lazy. So let me write it here by blue. The first thing that you need to do, you just call whatever given to you Pn. Okay, so you write this Pn. Now, the first thing that we are supposed to check is what? P of 1. Okay, it means that these are part of the points that I want to give you. Okay, so you have to write P of 1. P of 1, how should I write that? It means replace n with 1 everywhere. The right hand side is usually easy. I replaced n on the right hand side with 1. And what happens to the left hand side? The left hand side only contains one term, yes? And is it true or false? It is true, because 1 over 2, this is also 1 over 2. It's true. Okay? But you need to write that sentence in the exam, but if it is not exam, you don't need to worry. So you say that let k be a natural number so that p of k is true. We prove that p of k plus 1 is also true. But let me just write this. P of k is what? 1 over 2 plus 1 over 2 times 3 plus 1 over 3 times 4. And then I continue, I reach to 1 over k times k plus 1. I just replace n with k. This part is extremely simple. You don't even need to think. Just replace every n with k. And what is important, right in front of it, assumed to be true. And I hope that I could convince you. Assumed to be true is not the case, is not the same as it is really true. Assumed to be true. Okay? Now, p of k plus 1, you write it down. Here you have to be a little bit more careful when you want to replace every appearance of k with k plus 1. For example, the right-hand side is extremely easy. I replace k with k plus 1, so the numerator becomes k plus 1. What happens to the denominator? K plus 1 plus another 1. So it becomes k plus 2. Okay? And then just write it for k plus 1. So 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. And then you continue. It is what? 1 over every k should be replaced with k plus 1. So this one becomes k plus 1. This one becomes k plus 1. But I see there is another 1 there. So this becomes k plus 2. Then this I expect you to write. To be proven. So these two sentences, it shows that you actually know what you're doing. Okay, but I will of course solve a little bit more diverse problems than these sums with mathematical induction next time. So from here, then you have to think what to do. But at least the good news is that you are not empty-handed. If I ask you prove this, you have to prove this. But if I ask you to prove this, you are not empty-handed. You have something in your hand. Okay, so you can use this to prove this. Directly, if you want to prove it, you don't have anything in your hand. You need to be so smart to find a way to prove it. Okay, so that is the power in mathematical induction. Okay, then I want to wait for you because I hope that now you have enough experience. My goal is to prove this expression is equal to that expression. So what is your suggestion?
We take the pk, the right hand side, k divided by k plus 1, and add it to 1 divided by k plus 1 times k.
Exactly. So if you want to write it properly, write it in this way. Okay, what you said is completely correct. So you concentrate on proving this equality. One way of proving equalities is to start from the left-hand side, do legal mathematical things, and reach the right-hand side. So what I do, I will write left-hand side. And from the experience you got so far, you know that when you write the left-hand side, yes, and then I go up to level k plus 1, okay, so I go to level k plus 1, it means that I am here. But you know that if you go this pattern one at a time, when you reach to level k plus 1, even though it is not clear here, but you know that the previous step has also been covered, yes? So this means that what is the previous step that you don't see there is just k times k plus 1. Yes? Is that understandable for everyone? Okay. Now, my goal, this is exactly the left-hand side that you see here, which I added this to manifest itself here. So then I want to go from here and show that this sum is equal to this. Okay, what can I do? I am not empty-handed. That is the good news. Instead of this one, I can write something. What is that something? It is this one, which is assumed to be true. So instead of this big part, which was my main problem, I take it and write it as k over k plus 1. This is written for that. Yes? And now the rest of it I copy and paste. From here, there is nothing that I can do. You have to rely on your algebra. So you should be able somehow to combine these, okay, and reach to the right-hand side. So what is your suggestion? I have two fractions, but I see my goal is to reach to one fraction. So it motivates me to take the common denominator. Yes?
Multiply that for k plus 2.
Yes, I want to make the denominators the same, so I have to rescale the first one in a way that the denominators become the same. So how should I rescale it? I multiply it by k plus 2, so that the denominator of this one becomes this, but when I multiply the denominator by this, I have to multiply the numerator by this as well. And then what happens? It is k plus 1, k plus 2 over 1. Yes, this is the first step. And now the denominators are the same, so I can take the same denominator here, and I start adding the numerator of that one to that one. So it becomes k times k plus 2 plus 1. But still, I need to do something, because this expression is not still equal to this one. So hopefully we can continue if we haven't done any mistakes. So what do you suggest?
Divide k plus 2.
No, you cannot divide that. Yes, because this is a factor, I agree. This is not a factor of the numerator. And this is the very serious mistake, because if you cancel that one accidentally, you get the correct answer. Yes, so that's wrong, yes? So you see, if I have 2 times 3 plus 1 divided by 3 times 5, I cannot simplify this 3 with that 3. Yes, this is wrong. Okay, so what should I do then? Okay, I don't know what to do, so I multiply. So it becomes k squared plus 2k plus 1. The denominator I don't multiply. So that is, I hope that you have learned this in matrices. So if you want to simplify fractions, you don't need to multiply the denominators, but you have to start factorizing. But it is easy to factorize the numerator. What is that?
K plus 1.
K plus 1 squared. Yes? So this becomes k plus 1 squared, and then divided by k plus 1, k plus 2. Do you agree? And now, this can be simplified with that, because this is a product. K plus 1 to power 2 means k plus 1 times k plus 1. So I can't simplify the common factors. So what is left in the numerator is k plus 1. What is left in the denominator is k plus 2. Is it really what I want? Yes. So that's the right-hand side. Okay? So I hope that you really understand this, because this is my goal. Sooner or later, you will learn this trick. But I don't want you to do it automatically without understanding. Yes? Because I want you to understand where is the power here. You see, if I ask you calculate this without giving you anything, it is hard. But now that you know this part is equal to this, calculating this sum is just adding two terms. So you see, this is a very powerful tool in the hand of mathematicians to prove statements regarding natural numbers. Okay, so the next lesson, I will not teach you anything, but I will give you a little bit different problems that you can solve using mathematical induction to prove mathematical inductions. Any questions? No? Okay, thank you.